So for DC generators, we talked about these different types, just like the DC motors, separately excited generators, shunt generators, series generators, cumulatively compounded generators, and differentially compounded generators. A performance characteristic for generators would be the voltage regulation, as opposed to motors, where in the motors we talk about speed regulation. So voltage regulation in DC generators would be associated with V no load minus V full load over V full load. And if you want to basically express that in percent, you would multiply that by 100. A positive VR, as the formulation shows, would indicate a drooping voltage current characteristic, and a negative VR would indicate a rising voltage current characteristic. So in general, we don't want VR to be drooping. And if possible, we want that to be around 0. So if that's around 0 or just a few percentages, that would be the ideal case. Prime mover would be the mechanical power source associated with the generator. So we need some mechanical source to rotate basically the rotor of the generator. And those would be steam turbines, diesel engines, or electrical motors. The applications of DC generators are in the renewable energy systems. In general, they're not as much used as AC generators these days, but there are still some applications. That's why we need to go through some basic and fundamentals of DC generators. The first one would be the renewable energy systems in small scale wind energy systems or hydroelectric microgeneration. Also in transportation and automotive industry, they're used in hybrid and electric vehicles, aircraft power systems, ships and submarines. In industrial and commercial applications, they would be used in welding machines, backup power, emergency systems, UPS systems. In scientific and research applications, electrolysis and chemical processing, lab and test equipment. In military and defense, so for portable DC generators to ensure reliable and stable DC power in critical defense applications. The equivalent circuit would be associated with a field and an armature. Now, the upper figure is showing basically the equivalent circuit of a DC generator, including the adjustable resistance in the field circuit, and the V brush, which is associated with the voltage drop in the brush in the commutation system. We can basically come up with a more simplified basically circuit, which includes the adjustable resistance in the field circuit like this, and also neglects the V brush if that's not too much. So that would be figure 943. That would be a more simplified basically version. Now, depending on the type of motor generator, whether that's a separately excited or shunt, or series, we would need to combine these circuits together in different ways. So the first one would be the separately excited DC generator, where the field circuit is quite separated from the armature, and basically E versus or V versus IL, that's the performance characteristic associated with the generator that shows the terminal voltage with respect to the load current. So if you're not, we are not considering the weakening of the field associated with armature reaction, then the difference between the VT and EA would be in RA, as this equation 941 shows, which shows a linear drop, IA drop. So at no load, obviously the VT, the terminal voltage, would be the same as EA, armature voltage. But as the load grows, basically we get that voltage drop. Now, when you are including the armature reaction, then in addition to the RA-IA drop, you would have an armature reaction drop also, which could be nonlinear. So in general, as the load is growing or the load's current is becoming more and more, we can get this basically nonlinear characteristic. Now, the methods to control the voltage in the separately excited DC generator would be to either through basically the general equation of EA is equal to K phi omega. If we are able to change the omega or the speed of rotation, then we would be able to change EA, which would in fact result in changing the VT. However, the prime movers are often limited in their speed, so we cannot greatly change omega in many applications. Therefore, the more practical way of basically controlling voltage would be to change the field current. So that would be by changing the RF, the effective RF, to impact IF, and then IF would impact phi, and that phi would impact EA, and then that would result in a change in the terminal voltage. So, in fact, considering the fact that basically, if you look at the VT versus IL, and the VT over IL, that basically would be kind of that slope would be kind of constant. RL is the loads basically resistance, which would be VT over IL. Basically, you could be on different points on this line. However, the point of intersection, that would be the point associated with the working region of your generator. So in the case that your VT versus IL characteristic is like this line, drooping line, then the point of intersection, that would determine basically how much the load's current would be. Now, by changing that or controlling the voltage, we practically mean that we're going to shift that VT, that drooping characteristic, a little higher or lower, and that would determine now how it could change basically the behavior of the machine. All right, so we did an example last time on the separately excited generator. We considered a separately excited generator rated at 172 kilowatt, 43 volt, 430 volt, 400 amps, 1800 RPMs. And this is the circuit and the magnetization curve shown in here at 1800 RPM. These are the parameters of the generator. In part A, if a variable resistor in the generator's field circuit is adjusted to 63 ohms and the generator's prime mover is driving at 1600 RPM, what would be the generator's no-load terminal voltage? So we don't have any load on the terminal, therefore EA would be the same as VT. So in part A, if you have that overall field circuit of RF plus R adjustable equal to 83 ohms, then that would create an IF equal to 5.2 amps. Now, through this magnetization characteristic of your generator, for 5.2, you would get a 430 volts. However, we should pay attention to the fact that this curve has been extracted at a certain, basically, rotational speed in your rotor, which is 1800. And now that we have an 1600 RPM, therefore, we could determine now what would be the EA, the actual EA, through this equation 913. So the actual voltage on the armature would be 382 volts, which would fall on the terminal since there is no load. So this was the first part of the problem. In part B, we wanted to know what would the voltage be if a 360 amp load were connected to the terminals, assuming that the generator has compensating windings. So when the generator has compensating windings, it means that there is no armature reaction. So for part B, we could use the characteristic like as is. VT is equal to EA minus RA IA, which would give us a 364 volts in these conditions. Now in part C, we have the same load. However, we are assuming there is no compensating windings, or in other words, there is armature reaction existing, assuming that the armature reaction's effect at this load is 450 amp turns. So considering that 450 amp turns, we can come up with the IF star, which would come from the IF in the circuit minus FAR 450 over NF, which is a number of turns in the field circuit. So this would give us a 4.75 amp effective, basically, in your armature circuit. So from the magnetization curve, now this 4.75 would give you a 410 volts, as can be seen in here. So again, we have to look at the practical conditions where the generator's speed is 1600, because this basically curve has been found at 1800. So therefore, this gives you a 364 volts, which now you need to put in here to find out the actual terminal voltage in this case, which would come up as 346 volts. So this was part C. In part D, what adjustment could be made to the generator to restore the terminal voltage to the value found in part A? In part A, basically, the terminal voltage was found at 382 volts. Now, we are at 346. So one way to do that, we would be able to adjust the rheostat in the field circuit in order to do that. And in part E, it's asking how much field current would be needed to restore the terminal voltage to the no-load value, practically speaking. So for that, since we want 382 volts, then we would, in this equation, find out what should be the actual voltage on the armature, which finds it out at 400 volts. Since we have RA and IA, we know what IA is. IA would be the same value of 360 amps that was used in part C. So that gives us a 400 volts. Now, to get that 400 volts at 1600 RPM means that in the equivalent circuit, we should have really a 450 volts. 450 volts because this curve is associated with the 1800 RPM. So from here, at 450 volts, we would come up with 615 basically amps in the field circuit, which can give us basically an estimation of how much the adjustable resistance should be in the field circuit, which would be around 50 ohms. We're having the magnetization curve for a separately excited DC generator, the open circuit armature voltage versus the field current at 1800 RPM, which is described by IFEA 1800 function below. So this is the function. All required data is shown in the following code. Answer the following questions, assuming no armature reaction. So if the generator is operating at no load with the rated speed, what is the range of voltage adjustment achieved by changing our adjustable? All right, let's look at this problem first part. So we're having unrated, these are the inputs to the problem. VF is 120 volts, RF is 20. Our adjustable minimum is 0, our adjustable maximum is 40 ohms. And we have, and minimum in the machine is 1500 and maximum is 2000 RPM, okay? So first of all, it's asking if the generator is operating at no load with the rated speed, what would be the range of voltage adjustment achieved by changing the R adjustable? So we know that if you increase the R adjustable, then we would be able to reduce IF, which in turn would reduce phi, which would reduce EA, right? So this gives us basically this idea that our adjustable minimum would be for the case where we want to have the maximum voltage, and we would use our adjustable maximum to gain the minimum voltage. That makes sense. So looking at IF min, the minimum current that we can have in the field would be VF over RF plus our adjustable maximum. Now we can put that IF minimum in the curve to find EA. However, this EA is EA0, which means that that's based on the curve at the N rated equal to 1800 RPM. And IF max would be when VF is divided by IF plus our adjustable minimum. This gives us the EA max, which we need to basically also consider the fact that this voltage is at 1800. So based on the fact that in the problem, we're saying that the machine is operating at no load at the rated speed. Therefore, these would be the two voltages that we would expect, the minimum and the maximum voltage. In part B, again, it's asking if the field rheostat is allowed to change in that operating range, and the generator's speed is allowed to vary from 1500 all the way up to 2000 RPM, what would be the maximum and minimum no-load voltages in the generator. So now we have another factor in here, which is basically we're allowing the prime mover to change its speed between 1500 to 2000. So that's another factor that can impact the voltage. So the 1500 obviously is the minimum. 1500 would be associated with the minimum voltage when R adjustable is at its maximum. And 2000 would be associated with the EA maximum when R adjustable is at its minimum. Okay, so part B. We know EA minimum. We want it to be EA 0 minimum times N minimum N rated divided by N rated. So this gives us an EA minimum, and EA maximum would be associated with a EA 0 maximum, which is at 1800. And in order to basically find that at 2000 RPM, we would use this. So we would divide it, multiply that by N max over N rated. So in general, this would be at 1800 RPM, this is the minimum and the maximum EA that you can get. Now, EA minimum at 1500 would be 66.25, and EA maximum would be found at 2000 RPM, equal to 150 volts. So I also wanted us to go over the plotting. So I have to uncomment this part. This part is plotting the curve. So for the curve, you can see that the curve can go from IF of 0 all the way up to 7. So in order to plot that curve, we can go also through an IF vector, which goes between 0 all the way up to 7 in basically some increments. And that increment, if it is less or smaller, that would give us a better granulated basically curve. So I chose it to be at 0.01, but I mean, you can put it at a bigger number, like 0.1. And for each point on the IF vector, you would get an EA. So therefore, EA, you can have an EA vector with the same number of components. So I put that all to zeros at first. And then I loop through all the basically IF vector points and find out its associated EA value. And then in the end, I can go ahead and plot this and put the right labels for this curve. So let's do it and see what we get. Yeah, this is the curve that I got. As you can see, this is not as smooth as the curve that you might find in books, and that's because we just approximated the curve through a few points, and we used interpolation, linear interpolation between the points to come up with the points that are between the two actual points on this sample table. Now we can also plot it by points. So if I put, for example, a star, you can see that it's plotting basically the curve using these dot points that I wanted them to be star. You can change that to be dots, for example. All right, now let's go to the next generator, which is the shunt DC generator. In the shunt DC generator, you would have basically this circuit. So the field circuit would be on the terminals of the generator. So if this machine was working as a motor, you could basically provide the voltage here, and you would get an IF or the field current right away in order to be able to operate this machine. But when the machine is a generator, then you don't have any voltage at the beginning to work with. So therefore, you don't have any IF. So how would you be able to run this machine as a generator? So you would really need to use the residual, basically, flux that is existing in the machine prior to its operation, and look at basically this EA and VT versus IF. And also at the same time, if you put this line, which is RF equal to VT over IF, that's the slope of the excitation circuit associated with the RF. Now, if you just intersect these two, this would give you basically a way to analyze how this machine can start. So basically, through this residual EA, you would get a little bit of voltage at the very beginning at this point, and this will translate into a little bit of basically IF, or the excitation current, through this line. And that small current that is flowing in the field now gives you a chance to basically have a bigger voltage, and that bigger voltage induced in EA would now translate into a little bit of more IF. And as you can see through these two curves, the intersection points, you can find out how the voltage can be built up in this machine. So that's basically the way that you would be able to run this motor. Now, if you come up with a case where the adjustable resistance in here is too big, so that this curve would rotate, this RF line would rotate and be somewhere like here, then you wouldn't get a chance to be able to run this circuit. So you always need to make this RF small so that you get a chance to have these intersection points between this curve and this line, if that makes sense, in order to be able to start this generator. The terminal characteristic of this shunt generator would be kind of similar to the separately excited once it's started operating and the voltage has been built up. If you do not consider the basically field weakening effect because of the armature reaction, you can assume that there would be something like an RAIA drop. And additionally, if there is a field weakening effect because of the armature reaction, this would be the practical basically line that you would get that could become nonlinear as the load is growing. And the same methods would be used for controlling the voltage, changing the shaft speed, and changing the field resistor for the generator. So the same concepts is correct in here also. Now, you can have a visual way to analyze the operation of the DC generator in the case where there is no armature reaction. So if you look at basically the two curves, one is EA, or the magnetization curve of your generator, which shows you the EA versus IF, EA versus IF, and then you intersect that with the VT versus IF, which is VT versus IF would be basically the same as the slope of the excitation circuit. If you intersect these two, then the difference between these two, EA and VT, would be RAIA. RAIA. So through this, you can come up with a visual method. So take in the practical considerations, if there is an IA existing in your armature, the RAIA would be associated with the voltage drop, which would be like a line segment. If you just scroll that line segment between these two curves, between the EA and this VT versus IF line, right basically at the point that this line segment would be, one side of it would be on the EA curve, the other side would be on this line. That would determine the VT, the actual VT in which you are operating, if that makes sense. So that line segment could also be true at this point, but we usually consider basically the actual working consideration, operating conditions of the machine is when you have the biggest voltage possible on your circuit. So we would consider that. You can come up with this to determine the VT versus IL characteristic. So through each RAIA drop or each working condition, you come up with the VT, and then you would get the actual IL. So there is a difference between IA and IL in the shunt machine, right? IA would be different from IL. So if you really want to find out the VT versus IL, that would be the real basically work that needs to be done. You find the RAIA drop. From there, you find the VT. So that would be one of the points, but you also need to find out IL and then basically find and then draw the right VT versus IL curve, if that makes sense. So this gives you that basically kind of nonlinear operation of the machine. Another RAIA drop versus its actual IF would give you another point. So you can see that by connecting these lines, you would get an actual representation of VT versus IL curve. And this could go into some collapse if the IL is becoming too much, as you can see. This is the case when there was no armature reaction. Even when there is no armature reaction, you can see that you get a curve. It's not completely linear. So it's not only RAIA that would come up with a straight line, like the case that you had in the separately excited generator. In the separately excited generator, if there is no armature reaction, this would be the relationship that you get because IA would be the same as IL. But keep that in mind that in the shunt generator, now there is the effect of IL not being equal to IA. So therefore, you would need to use this method in order to come up with the actual characteristic of the machine. Now, if you have armature reaction, you would be adding a demagnetization also. So coming up with the same two curves, intersecting them. Now you would have a triangle that you need to fit in between these two curves. So this basically side of the triangle would be the same RAIA drop. And this one is associated with the demagnetization. So you would, in other words, you would need to come up with the IF, the equivalent IF drop. And then this creates a triangle that you would need to scroll through between these two curves until you see one side of this triangle is on the EA curve and the other basically point would be falling on this line. So that would be determining your actual operation of the machine. So that's VT with load. And this is EA with load. And this is basically the way that you would be needing to use visually in order to determine the operating conditions of the machine. Now, for the series generator, we see that the field winding is connected in series with the armature. Since the armature current is much higher than the shunt field, the series field winding would be having fewer terms, but it has to use thicker wires to handle the high current, obviously. The magnetomotive force is given by Ni, always, meaning that the same MMF can be achieved with higher current and lower N in this series generator application. In terms of design considerations, since the series field must have very low resistance to avoid excessive voltage drops, and that can be realized by basically having thicker wires, right? And then the full load current flows through the series field, necessitating a robust design. So this is the equivalent circuit. The difference between VT and EA would be determined by the voltage drop associated with the summation of RA and RS and times IA. So the terminal characteristic of the series DC generator would be different from those of the separately excited and the shunt generators. So if this is showing the E versus the voltage versus the current of the machine would be the same as the armature current, and it's the same as the load current, the same as the series field current. So these are the same on the current side, but considering the magnetization curve of the machine under no load conditions, you would have an RA plus RS times IA drop. So this difference would determine the difference between EA and VT. So having that voltage drop, you can see that the terminal voltage characteristic would be something like this. And basically, this is the case that you don't have any armature reaction. If you add the armature reaction on top of that drop, then you would see that the curve could get into a more nonlinear compared to basically what you had in the case that you didn't have the armature reaction. So this characteristic is very appropriate for certain types of applications, like arc welding. Before welding begins, the electrode contact results in high current. And as electrodes separate, voltage rises steeply while current is still high. So in general, in applications when you require both high current and high voltage in a certain region, you would be able to use the series DC generator. All right, so the same way that you had a compounded DC generators, you can have compounded motors, you can have compounded generators, which could be connected in cumulatively or differentially compounded ways. So this is showing basically a long shunt connection of a cumulatively compounded DC generator. The figure on the right-hand side is showing a short shunt connection So F net, the total basically magnetomotive force in the machine is coming from the field plus the series minus the armature reaction. From this equation 948, you can come up with the effective or IF star, which would be your actual IF plus NSE over NF times IA minus F armature over NF. NF is the number of turns in the shunt circuit, and NSE is the number of turns in the series circuit. So the equations of the machine are pretty straightforward through these circuits. And we really need to look at basically the characteristics of the cumulatively compounded DC generator with respect to the shunt machine. So if you look at the VT versus IL characteristic of the machine, for the shunt machine, you would get something like this, and there is no SE or no series field. Now, depending on the number of turns in the series winding, if you have a little bit of or a small number of NSE, then the VT versus IL would still be drooping, but not as high as the shunt. So in this case, we call this the undercompounded case. If you try to keep the VT versus IL as flat as possible, so in the no load condition with respect to the loaded condition, then you can use a moderate number of NSE turns in the series winding. And if you increase the number of NSE or the series field windings, you can get to an over-compounded case. So really that series windings in this case gives you a means to be able to have a better voltage characteristic or terminal characteristic in the generator. That makes sense. For the differentially compounded generator, though, you would get a worse, basically, characteristic with respect to the shunt generator, as can be seen. And these are basically the relationships. The series field winding would be subtracted from, just like the armature reaction from the shunt field, if that makes sense. So mostly we would use basically the cumulatively compounded rather than the differentially compounded generator because of the fact that, as you can see, the characteristic here is very poor and can become nonlinear very fast.